Hello everyone, in this video we are just going to test the UART serial communication in the microcontroller TM4C123 GH6PM with help of this Tiva C series launchpad development board. Let's get started. So let us now discuss about the agenda for this video so that you will get to know what you are going to learn in this video. So the first and foremost things that we are going to discuss is we are just going to discuss about the various kinds of UART ports in TM4C123 series microcontroller, and the second thing is we will be configuring the UART port of Tiva series microcontroller, that is this TM4C123 series microcontroller, and after that we will be writing our program for transmitting byte of data in UART communication, and later we will be testing the Uart communication with the help of Tiva C launchpad development board. So we will be connecting our Tiva C launchpad to the PC, and then we will be testing the UART communication program that we are writing right over here. We will be testing whether the program that we wrote in the third step is functioning properly. So that as a result of this video, you will be able to configure the Tiva C series microcontroller UART port for transmitting data over the UART line. So this is what the agenda that we are going to follow in this video. So let us get started with the first point, that is UART ports in TM4C123. So before that, let me just open the KEIL Microvision IDE and let us create the project for our microcontroller TM4C123. I am just opening the KEIL Microvision IDE. So you can clearly see the project has been created and the main.c file has been created for the project, and now let us start write the programming for the UART communication. And you can clearly see this is a program that we wrote in the lecture of interfacing push buttons with our microcontroller TM4C123 GH6PM. So I hope you remember this program that we wrote in that lecture. We just wrote this program step by step in that video. So I am just going to copy this program and I am going to utilize and upgrade this program for the UART transmission process. So I am just going to use two buttons in the Tiva C series launchpad development board. So that is why I am just copying this code. If you are not sure about this program, just move on to the lecture of interfacing push buttons with the microcontroller TM4C123 GH6PM. I have already written this program step by step in that video. So I am just going to copy this and I am pasting it right over here. But the things that is available right over here is very common things. That is, here I am just unlocking the Gpio port of Gpio, and then I am just configuring two push buttons, that is PF0, PF4 push buttons and PF3 LED. So I am just configuring the pin PF3, which is connected to green LED in my Tiva C series launchpad development board, and I am configuring this PF3 as output. And regarding the PF4 and PF0, I am just configuring these two pins as inputs, and I am enabling the digital enable pit of these three pins, PF0, PF3 and PF4. And regarding the programming logic, let me just come into the while of 1. Here what I will do is I am just checking whether the button 1 is pressed, that is button connected to PF4 is pressed. If it is pressed, I will turn on the green LED, and if the button 2 is pressed, I will turn off the green LED, that is the same LED. So this is the process. Let me just build this project. You can see I am getting 0 errors and 1 warning. That is not a problem. Now I am just dumping this code to the microcontroller. You can see the code has been successfully flashed to the microcontroller. I have already connected the Tiva C series launchpad to my PC through micro USB cable. Now let us check the output in the hardware. You can see this is the Tiva C series launchpad development board. You can see this is the Tiva C series launchpad development board to which I have flashed the program. So this one is the SW1 push button which is connected to PF4, and this one is the SW2 push button which is connected to PF0. And as per our programming logic, when I press this button, the green LED must be turned on. So here is the LED. This is a tricolor LED, red, green and blue LED. So green LED on this LED will be turned on whenever I press this button, and whenever I press this button, the green LED will be turned off. This is the logic. I am just resetting the board. This is the reset switch. Now you can see the green LED is turned on, off, on, off, on, off, on, off, on, off, on, off. So our programming logic for interfacing push button is working fine. So now what I am going to do is, using this program, I am just going to alter or add several programming lines for transmitting some data through UART line. That is, whenever I press this button which is connected to PF4, I will be transmitting the character small a in the UART transmission line. And whenever I press this button which is connected to PF0, I will be transmitting the character small b in UART transmission line. So this will be my programming logic. Whenever I press this button, I will be transmitting the character small a in UART line, and whenever I press this button, I will be connecting or transmitting the character small b in UART transmission line. A, B, A, B, A, B will be transmitted whenever I press these two buttons. So this will be my programming logic that I am going to build in this video. So let's get started. Now let us try to open the datasheet of the microcontroller TM4C123 and let us study in detail about the UART ports available in the microcontroller. Now let us try to open the datasheet of the microcontroller TM4C123 for understanding the available UART ports in that microcontroller. So in the datasheet, just click on the Universal Asynchronous Receivers or Transmitter tab, and here you can clearly see this microcontroller TM4C123GS6PM includes 8 UART ports. So totally we are having 8 UART ports, and you can utilize all the 8 UART ports at a time in this microcontroller. And these UART ports are allowing you up to a baud rate of 5 Mbps, and all the regular speeds are also supported along with 4 different data bit modes, that is 5 bits, 6 bits, 7 bits or 8 bits. You can choose between these 4 bits as your word length for your UART communication, and usually I will be choosing the 8 bits mode UART communication, and the standard baud rate that I will be configuring is 9600. And let us see what are all the pins available for UART communication. And in this table you can clearly see all the pin details are mentioned. UART 0 RX is PA0 and TX is PA1, and UART 1 RX is PC4 or PB0, TX is PC5 or PB1. You can use either one of these two pins. UART 2 RX is PD6 and TX is PD7. UART 3 RX is PC6 and TX is PC7. UART 4 RX is PC4 and TX is PC5. UART 5 RX is PE4, TX is PE5. UART 6 RX is PD4, TX is PD5. UART 7 RX is PE0 and TX is PE1. So I am just going to configure this UART 0 because the default UART port available in the Tiva C series launchpad development board is connected to the UART 0 line of the microcontroller. So if I am using this UART 0, or the advantage of using this UART 0 in my cases, I need not use any external hardware for visualizing the data that is transmitting from the UART port to the PC serial UART terminal software. So I can just directly plug the micro USB cable from my PC to the Tiva C series launchpad development board, and I can just directly connect the port, that is UART 0 port of the microcontroller, to the serial terminal software in my PC. So other than that, if I am using any one of these available 8 ports, I just want to use a detail converter between this port and the PC USB cable, or I just want to use a USB to UART bridge. So for avoiding that, I am just using the UART 0 available in my Tiva C series launchpad development board, that is the TM4C123 GS6PM microcontroller. And the RX pin of the communication is PA0 and TX pin is PA1. So make sure and note it down. Now let's move into the programming for configuring the UART communication. So these are all the steps that we need to follow for configuring the UART port of the Tiva C series microcontroller. And as I already mentioned, I am just going to use the UART 0 line of the microcontroller for UART communication, that is PA0 and PA1 will be configured as the UART RX line and as well as the UART TX line. So you can clearly see, as I have already shown you a table, UART 0 RX is PA0 and UART 0 TX is PA1. So we are just going to use this UART port of microcontroller, since because it is connected to the default UART communication port, which is connected to the USB port of the PC. So we need not use any external hardware. I am just using this UART port other than any other UART ports available out of all the 8 UART ports available. So this is the UART port that I am going to configure. So the first and foremost configurations that we want to do is system control configurations required for UART port, and the second configurations that we want to do is Gpio configurations required for UART port, and finally we just want to perform the UART port configuration, that is the baud rate as well as the speed and communication parameters configuration. So these are all the 3 different configurations that we want to do. So under the system control configuration, the first and foremost thing that we want to do is we just want to enable the clock of UART port used. So as soon as you hear about the clock, you just want to enter into the system control section of the datasheet. So here come under the register map, and here you can find a register named RCGC UART. So this is the register which is useful for configuring the clock of the UART communication. So using this register, you can just enable or disable the clock required for the peripheral UART. So I just want to move to the 344 page for this register. So this is the register. You can clearly see it is a 32-bit wide register, and we will be able to only access the LSB 8 bit starting from bit 0 to bit 7, and each bit is meant for a separate UART communication. As I mentioned earlier in this video, we are having a total of 8 UART ports starting from UART 0 to UART 7, and each bit in this register is meant for enabling or disabling each UART port. That is, the bit number 0 in this register is meant for enabling or disabling the clock of UART 0, and bit number 1 is meant for UART 1, and similarly bit number 2 is meant for UART 2, 3 is meant for UART 3, 4 is meant for UART 4, 5 is meant for UART 5, and 6 is meant for UART 6, and finally 7 is meant for UART 7. So when I write 1 to the bit number 0 in this register, it will enable and provide a clock for UART module 0 in run mode. So I just want to write 1 to this 0th bit of this register with the help of the pointer UART 0, since I am using the UART 0 peripheral of the microcontroller. So this is the pointer UART 0, and I am going to point to, so this is a system control configuration. So for that you just want to use sysctl pointer, and using that you just want to point to rcgc uart, and I want to enable the bit number 0 for uart 0. And the second thing that we want to do is we just want to enable the clock for the Gpio port used. So the Gpios that I am going to use for UART communication is PA0 and PA1, right? So I just want to enable the clock for port A of my microcontroller. So that can be done with the register called RCGC Gpio. So this is the register, and we know this register as we have been using this in a while in almost in all the Gpio related videos. So it is also having a 32-bit wide data, and we will be able to access only the 6 bits starting from bit 0 to bit 5, and each bit is meant for a particular port. Bit 0 is meant for Gpio A, 1 is meant for B, 2 is meant for C, 3 is meant for D, 4 is meant for E, and finally bit number 5 is meant for Gpio F. And if I write 1 to the bit number 0, it will enable the clock for Gpio port A, which I want to do. So I am just enabling or writing 1 to the bit number 0 of this register also with the help of same pointer, RCGC Gpio, and I am going to write 1 to bit number 0 for enabling the clock of Gpio A. And that's all about the configurations that we want to do for system control registers. And the second configurations that we want to do is Gpio configuration. And as the first step, we just want to set the alternate functions for the UART pins to be high. So coming inside the datasheet, let's move on to the Gpio part, and inside the register map you can find the Gpio AFSCL register. So this register is available in 671. So this is the register, you can clearly see. This register is specifically used for enabling the alternate function method for a particular Gpio pin. So if you are using a particular digital Gpio pin as alternate function such as ADC or UART or SPI or I2C, you just want to set the particular bit number in this register for that pin to be high. So in our case, I am just going to configure the PA0 and PA1 as UART line. So I just want to write 1 to bit number 0 and bit number 1 with the help of the pointer Gpio A, since I am configuring the Gpio A, that is port A of the microcontroller. You can see as usual it is having only the LSB 8 bits to be active, and all the other bits are reserved. We cannot write or read to these bits, and each bit is meant for a particular pin in the corresponding port. If 1, that means the associated pin functions as a peripheral signal and is controlled by a alternate hardware function. So I just want to write 1 to bit number 0 and bit number 1 of this register with the help of Gpio A pointer, since I am using PA0 and PA1 as the UART port. So I just want to point to AFSL register, and I want to write 1 to the bit number 0 and bit number 1 for PA0, PA1. And as the next step, I just want to set the mode in Pctl register. So mode can be set once the AFSCL bit is high. So that is set in the register called Pctl. Let me just open that register. So this is the Gpio port control register. This register is used in conjunction with the Gpio AFSL register and select the specific peripheral signals for each Gpio pin used. So it is also useful for providing an additional hardware function for a particular Gpio pin. You can clearly see from this table for the PA pin 0 and 1, the default reset state is UART 0, and you just want to provide the Gpio Pctl state to be 0x1. so that it will be acting as a UART pin 0. So you can clearly see in this register it is having a total of 32 bits and it is subdivided into 8 different parts, 4 bits, and this LSB 4 bit starting from 0 to 3 is meant for pin number 0, and these bits from 4 to 7 is meant for pin number 1 in the port, and 8 to 11 is meant for pin number 2, 12 to 15 is meant for pin number 3, 16 to 19 is meant for pin number 4, 20 to 23 is meant for pin number 5, and 24 to 27 is meant for pin number 6, and finally 28 to 31 is meant for pin number 7. So I just want to write 1 to these 4 LSB bits, and also I just want to write 1 to these 4 bits from 4 to 7. That is, I just want to set 0th bit right over here and 4th bit right over here for the pins such as PA0 and PA1 with the help of Gpio pointer, so that I will be configuring the PA0 and 1 in UART mode 0 with the value of 0x1 for Gpio Pctl register. So this is a default value, so you just want to provide for configuring the particular pin as UART line Pctl, and I just want to configure or write 1 to bit number 0 and bit number 4. And next thing is I just want to digitalize these 2 pins. So for that we are having a separate register called digital enabled register. Let me just show you that. This is the register, and this register is also having 32 bits. Only the LSB 8 bits are readable and writable, and each bit in this register from 0 to 7 is meant for a particular pin in the port as per the pointer that you are using for the port. So if I write 1 to the bit number 0, the 0th pin of the port will be configured as digital IO, and if I write 1 to the first bit of this port, first bit of this register, then the particular port pin that is such as PA1 will be configured as digital IO. So I just want to do that. I'm just pointing this register with the help of Gpio pointer since I'm configuring the port A, and I'm just going to point it to DN register. 0 for PA0 and 1 for PA1. That's it. Gpio configuration is done along with system control configuration. So moving on to the next configuration, that is UART configuration. This is the configuration or very important configuration that we want to do for proper running of the communication UART in this microcontroller. And first and foremost thing that we want to do is we just want to set the baud rate in Ibrd and Fprd register. And if you have watched the previous video of UART communication working explained, that is serial UART communication working explained, in that video I have clearly mentioned what is baud rate and how it is functioning in transmission of data in asynchronous mode of this serial communication. So baud rate is a very important parameter in communication such as UART. So if you have not watched that video, please go back to that video and then come back here. So I have already provided the videos in a such order in my playlist, so I hope you will be learning in that order only. So I'm just continuing in this video. So as the first step, I'm just going to set the baud rate in Ibrd and Fprd register. Let me just open these 2 registers. So I'm just moving to the UART chapter in this data sheet, and under this chapter, and you can see these are all the 2 main registers which is useful for storing the baud rate, UART Ibrd and UART Fprd. And this Ibrd is useful for storing the fractional part before the decimal point, and this Ibrd is useful for storing the integer part in the baud rate calculation, and the Fprd register is useful for storing the fractional part for more accuracy. Let me just show you the calculations that you want to do. So these are all the 2 formulas that you want to use for calculating the value that you want to load to the Ibrd and Fprd registers for a particular baud rate. So you can clearly see Ibrd is equal to UART system clock divided by clock divider into baud rate. So let me just assume that I am just going to configure the UART communication in a standard baud rate of 9600. So the baud rate right over here is 9600 and this clock division is 16 and UART system clock is 16 megahertz. My system clock is running at 16 megahertz. So 16 megahertz is nothing but 0000000 divided by 16 into 9600. So when I solve this equation, I will be achieving the value that I want to write to the Ibrd register. So let me just open the calculator. (16 megahertz divided by 16 is 1 megahertz. Again divided by 9600 is 104.166666667. Since we cannot write this fractional part onto this Ibrd register, what we will do is we will just neglect this fractional part, and if you neglect this fractional part, we will be lacking in communication when you transfer a huge set of data. So for that purpose, for increasing the accuracy of communication in terms of baud rate, they have provided this fractional baud rate register. So here we will be substituting the fractional part and we will be loading this register with this value. So solving this equation, we will be getting a particular value, right? So that value will be stored in this register for increasing the baud rate of communication. So what I will do is I will just equate this into 64 plus 0.5. So I am getting 11.166666667. So this is the value of the Fprd. So what I will do is I will load the value 11 to this Fprd register. So in this manner, you just want to equate the formula as per the baud rate that you are using, and then you just want to split the fractional part from the answer that you got for the Ibrd register, and you want to substitute right over here the fractional part only. And regarding the fractional part in this result of this equation, we will be neglecting directly. So this Ibrd register is useful for storing the integer part of the equation provided right over here as per the baud rate that you are configuring, and this Fprd register is useful for increasing the baud rate accuracy by equating this fractional part. So that is why we are just going to add the value 11 to this Fprd and 104 to this Ibrd. So here I'm just going to use the pointer UART 0 since I'm configuring the UART 0, and I'm going to point to Ibrd register, and the value that I'm going to load is 104. And as the next step, I'm just going to use the same pointer for pointing to Fprd, and I'm going to load the value 11. So we successfully configured the UART baud rate for the communication UART 0 to be 9600 bits per second. And the next configuration that we want to do is we just want to set the word length for the UART communication in LCRH register. Here is the LCRH register, which is the next register. Here you can see the bit number 5 and 6. We are having WLEN bits. So these two bits define the word length for UART communication. So the casual word length that we will be using in UART communication is 8 bits. So we just want to transmit at least a byte of data through UART once you are transmitting. So that is why we are just commonly using 8 bits as the word length for UART communication. So we just want to configure these two bits to be 1, 1 or 0x3 for setting the word length to be 8 bits. So what I can do is I'm just going to point to UART 0 to the register LCRH, and I'm going to write 0x3 left shifted by 5 times. So I just want to write to the bit number 5 and 6. So I'm just writing 0x3, that is 1 1 left shifted by 5 times in this register. Or you can set individual bits 5 and 6 as a whole, that is not a problem. But now I'm setting as a whole. So now here I'm setting the word length to be 8 bits. And as the next step, we just want to select the clock source in CC register. Let me just find the CC register. Here is the UART clock configuration register. So in this register, we are only having 4 bits as a read or write bits, and all the other bits are reserved. We cannot write to these bits. And in these 4 bits, you can either write 0, 01 to 04, which are reserved, and then you can write 0x5 or 0x5 to 0xf, which are also reserved. So these two are reserved, you cannot write these. And if you are using the system clock, then you can write 0x0 to these 4 bits, that is 0000 to these 4 bits. But if you are using precision internal oscillator as the clock source, you just want to write 0x5 to these 4 bits. So in our case, I am just going to use the precision internal oscillator. So I am just going to write 0x5 as the data to this register. So I am just going to use UART 0 CC is equal to 0x5. So as the next step, I am just going to move to the control register of UART communication for enabling these 3 bits, that is UART enable, transmission enable and reception enable. So let me just move to that register. So in this register, mainly we are just focusing on UART enable bit, that is bit number 0, and transmission enable bit, that is bit number 8, and reception enable bit, that is bit number 9. So these 3 are the main bits that I am going to enable before starting the UART communication. But this is also a 30-bit wide register, and it is having a several number of bits which is having a separate processes. But now we are just going to enable only these 3 bits, bit number 0, bit number 8 and bit number 9. So bit number 0 is meant for enabling the UART communication, for bit number 8 is useful for enabling the transmission in UART communication, and bit number 9 is useful for enabling the reception in UART communication. You can see bit number 9 is UART receive enable, bit number 8 is transmit enable, and bit number 0 is UART enable. So I am just going to use the same UART 0, and I am going to point to CTL 0th bit, 8th bit and 9th bit. And that's all about the configurations that we want to do. We have completed the UART configuration, Gpio configuration for UART, and system control configuration for the UART. And one more thing is, I am just going to disable these bits before the actual initialization part. So I am just going to do that right over here. That's it, and we are done with the configuration part for UART communication. In addition to that, we have already configured the push buttons required for our project. We don't need the LED which is connected to PF3, but we are just going to use the 2 push buttons available in Tiva C series Launchpad development board, one for transmitting the character small a and another one for transmitting the character small b. So we are just going to do that. That is our programming logic that we planned. So you can clearly see this is the programming logic that we have written, and if I press the SW1 button, I will be turning on the LED PF3, and if I press the button which is called SW2, I will be turning off the same LED. So this is the programming logic. This was the programming logic that we visualized physically in the hardware just before in the beginning of the video, and now I'm just going to delete the programming lines available right over in the if conditions, and I'm going to write some programming lines right over here for transmitting the required characters through UART communication. So here for writing the data through UART communication, I am just going to move to the DR register of the UART communication, that is data register of the UART communication, and I am going to write the required value that I want to pass through the UART communication. And after that I am just going to provide a rough loop delay right over here for debouncing purpose. And in a similar manner I am just going to transmit a character B when I press the button 2, that is SW2, and here when I press the SW1 button I will be transmitting character small a through UART communication, and when I press the button 2, that is SW2 button, I will be transmitting the character small b in UART communication, and I have provided debounce delay right over here. And don't forget to add this debounce delay function. This is just a loop delay function, that is a rough delay function. And before transmitting the byte of data to the data register, we just want to make sure that no data is available in the data register. That is, the data that we are passing has been successfully transmitted before writing to the data register. So that can be found with a register called Fr register. So let me just open that register. So here is the Fr, that is UART flag register. So in this register we are having totally several 5 to 6 bits, and these are all the flags required for UART communication, some of the flags required for UART communication. And in this register we will be using only the TXFF flag available in the bit number 5. So let me just show you what is this flag. UART transmit FIFO full register, and 1 in this register means if the FIFO is disabled, the transmit holding register is full. If the FIFO is enabled, the transmit FIFO is full. So you can clearly see this is just a read only bit. We cannot alter the status of this TXFF bit, that is bit number 5 in this register. So we just want to check whether this bit is disabled or not. If it is disabled, we just want to load the data to the data register, and if it is not, we just want to wait until it is becoming 0 and we just want to load the data. So this is the process that we want to do. So what I can do right over here is I can just wait here using a while loop, that is UART 0 of Fr ampersand of 0x5 not is equal to 0. Sorry. And that's it. And you can clearly see here I am just checking for the bit number 5. Sorry, I just made a mistake. This is not 0x5. I just want to check for the bit number 5. So I am just going to write 1 left shift of 5. And if this result is not equal to 0, I will wait till it is becoming 0. If it is 0, I will write the data to the data register. And I am going to follow the same methodology right over here also. And that's it. You can see our programming logic is ready. Here we are just configuring the push buttons PF0 and PF4, SW1 and SW2 of the Tiva C series launchpad, and here we are just configuring system control, Gpio and Uart configurations that we want to do. and we are setting the baud rate of the UART communication to be 9600, and here we are just checking for the button 1 to be pressed. If it is pressed, we are just waiting until the FIFO is empty, and if it is empty, we are just loading the data to the data register. That is the required data, character small a to the data register. So if this button is pressed, the character A will be transmitted, and if this button is pressed, the character B will be transmitted. So this is the logic. I am just building this project. You can see the build is successful with 0 errors and 0 warnings. I am just going to dump the flash to the microcontroller. I have already connected my Tiva C series launchpad development board to my PC through micro USB cable. You can see the flash is loaded and the programming is done. Let us see the output in the hardware. Now I am just opening my Docklight serial monitor software. So this is the software that I am going to use for monitoring the serial data that is coming from the Tiva C series microcontroller from my Tiva C launchpad. And now I am just going to configure the port. As I have already connected this Tiva C launchpad to my PC through micro USB cable, just double click on this COM on the right top corner of this window. Here you can configure the COM port for the serial communication. You can see there is a serial USB device connected, that is nothing but my Tiva C launchpad. I am just selecting this COM8, and we have successfully configured the baud rate to be 9600. So I will not be disturbing all these things, and I am going to click on OK. Now for establishing the connection or for start the communication between the PC Docklight software and my Tiva C launchpad, just click on this play button in the left top corner of this window. You can see the communication has been established, and now as we have dumped the program to my Tiva C launchpad, I am just going to reset this board. And now when I press on this button, which is the SW1 push button, as per our logic, we must receive the character A, right? You can see the character A has been received in the Docklight serial monitor, and the UART transmission is successful in my Tiva C microcontroller. And when I press on this SW2 push button, I must get character B, right? Let me just press this. You can see the character B has been received in the serial monitor, and our logic is working fine. You can see I receive A when I press this button, and when I press this button I receive B. A, B, A, B, A, B, A, B, A, B. So our UART transmission program is working fine. So I hope we learnt all the things that I have written right over here in the beginning of this video. You learned what are all the UART ports available in the microcontroller. You learned how you can configure the UART port available in the Tiva C series microcontroller, and then we programmed our microcontroller for transmitting two different data using two different push buttons available in the Tiva C series launchpad development board, and finally we just tested the program that we wrote in the third step. So I hope you enjoyed this video. See you in the next video. Thanks for watching.